How are we doing today? Hopefully y'all are doing well. So today what we are going to be doing is finishing up our notes on Unit 3. This is the very last lesson that we have for Unit 3. I know it's been a long journey through our Unit 3, but this is the very last lesson for it. So for this, we are going to be covering light calculations, and you do need to make sure you've got your notes, something to write with, and then you will need a calculator as well. All right. So let's go ahead and get started on this. So, light calculations. So this is essentially us looking at light and trying to figure out what are the different things that we're talking about, be it frequency or energy or wavelength or whatever it is. We can use math to solve for those individual things. We can also talk about the number of photons that we can find in a given amount of energy of light. Okay, so for that, before we actually move on, let's talk about a wave. Now, a wave does have a couple of parts that you need to know. Those parts are the amplitude, right here, which is going to be the distance between that center point and the peak of the wave. Okay. You've got your wavelength, which is the distance from one wave to the next wave. So you go from the crest of one wave to the crest of another. That is also something else you need to know is the top of a wave is called the crest and the bottom of the wave is called the trough. All right, so those are your parts of the wave. Now, as a reminder, when we're talking about the EM spectrum, we know that we've got different frequencies and wavelengths. We know that things like gamma rays are going to have a very high frequency, but that also means a very short wavelength. And we know things like radio waves are going to have a very low frequency, but a very long wavelength. Okay, remember those two things are inverse. All right. So let's look at this. Now, if we're talking about wavelength, the symbol that we use is right here. It is lambda. Now, the wavelength is, again, the distance between two consecutive peaks or two consecutive troughs in a wave. So either way, you could look at the peaks or the troughs, should be the same, but it's the distance between two consecutive ones. All right. Then we've got frequency. Frequency uses nu for its symbol, and it's the number of waves that we have per second that are going to pass a given point in space. All right. Now, what we did is we were actually able to look at these and determine what the speed of light was. Okay, so we know that the speed of light equals our wavelength times our frequency. So again, wavelength is going to be that lambda symbol, and then frequency is the nu symbol. Lambda is going to be in meters. All right, so you do need to make sure that you are converting your wavelength into meters if you're given a wavelength, okay? Frequency is going to be in cycles per second. Now, cycles per second is s to the negative 1 or hertz. Hertz is just the name for s to the negative 1. Now, c is going to be your speed of light. We have already figured out what the speed of light is, so that is going to be a constant that we use. And the constant is 3.00 times 10 to the 8th meters per second. Okay, that would be your speed of light. Now, as a reminder, if we are talking about a short wavelength, we know that the frequency is high. All right, if it is a short wavelength, the frequency is high. If the wavelength is long, the frequency is low. So they are inversely related. You do need to keep that in mind. Okay, so let's look at this first example. We're going to start off small here. So it says the yellow light given off by a sodium lamp has a wavelength of 589 nanometers. What is the frequency of this radiation? Okay, so I have my speed of light formula, which is speed of light equals wavelength. That's not at all straight. Speed of light equals my wavelength times my frequency. Okay, so speed of light is wavelength times frequency. Now, this time I'm solving frequency. So to solve that, I'm going to divide both sides by wavelength. Okay, so then my frequency equals speed of light divided by wavelength. All right, so my frequency equals 3.00 times 10 to the 8th meters per second divided by my wavelength. Well, they told me my wavelength was 589 nanometers. Okay, well, first off, there's something that we need to keep in mind. Our wavelength needs to be in meters. So I'm actually just going to extend this and use this as a part of my dimensional analysis. So I need to convert my nanometers into meters. So I'm going to bring nanometers up. It's going to cancel that out. And I'm going to go from nanometers into meters. I know that there are 10 to the 9th nanometers for every 1 meter. All right, now that also is going to cancel out my meters there. So now what we can do is we can actually solve for our frequency. So frequency equals 3.00 times 10 to the 8th times 10 to the 9th divided by 589. Now when we do that, we're going to plug that into our calculator and you'll solve and get 5.09 times 10 to the 14th s to the negative 1. Okay, s to the negative 1 is the same as saying 1 over s. You could also put 1 over s or Hz for hertz. Any of those will work. All right. So now that we know how to solve our speed of light equation, so solving for frequency or wavelength, let's talk about some properties that waves can have. There's two things. The first thing is interference. So interference is when waves actually will cancel each other out or build each other up. So we can use interference to amplify a wave or cancel a wave out. Now, this is actually what you see happen in a noise-canceling headphone. Essentially, what they're going to do is they're going to send the opposite signal to it. It's going to cancel out that wave of sound that it is sensing, and so you will not hear that sound anymore. And so that's essentially what's going to happen with interference. You've also got diffraction, and diffraction is just when a wave encounters an obstacle, it's going to bend it. If I take a rock and I put it in the middle of the beach where the wave is going to crash onto the shore, that wave is going to go around that rock, right? When it encounters that obstacle, it will bend or diffract around it, okay? Now, in the past, when they talked about energy versus matter, they would always say they are completely two different things. They have nothing to do with each other. But in 1901, Max Planck, what he did was he found that if I heated up a solid, they absorbed and then emitted energy. Okay, well, we actually see that happen pretty consistently, right? So if I heat up a solid, it will start to glow, right? That is it releasing that energy. And what he determined is that that energy can be gained or lost in multiples, okay? And so in integer multiples. So he actually had a formula here, okay? And he actually came up with a constant, and that's 6.626 times 10 to the negative 34th joules seconds. That would be what we call Planck's constant. And here is our formula. What he said was that the change in energy equals that integer times Planck's constant times the frequency. And so n is the integer of 1, 2, 3, 4, whatever, 5, 6, 7, 8, 9, 10, whatever. And what he showed was that energy is quantized or put into these packets of energy, okay? Now, let's actually solve a problem that he would have had. So it says calculate the smallest increment of energy, so quantum of energy, that an object can absorb from yellow light with a wavelength of 589 nanometers. Okay, so we know that our change in energy equals the integer times Planck's constant times my frequency. So my change in energy equals my integer. Well, we wanted the least, right? The smallest, so 1, times Planck's constant, 6.63, times 10 to the negative 34th joule seconds. And then I'm looking for my frequency. But here's the thing, they didn't give me frequency, they gave me wavelength. So before I can actually solve this, I need to solve for my frequency. All right, so our formula for frequency, remember we use the speed of light equation. So speed of light equals wavelength times frequency. And then I rearrange that because I'm looking for frequency. So divide both sides by wavelength. So my frequency, my frequency equals speed of light divided by wavelength. Now plug that in. Frequency equals 3.00 times 10 to the 8th meters per second divided by our wavelength, 589 nanometers. Convert that from nanometers into meters. This is the same problem we just solved in the previous one, right? Okay. And we are going to get 5.09 times 10 to the 14th s to the negative 1. Well, now I can plug that into my formula here. So 5.09 times 10 to the 14th s to the negative 1. S to the negative 1 is again the same as dividing by s. So I'm going to plug that into my calculator. And what I'll find is 3.37 times 10 to the negative 19th joules. So that would be my change in energy. All right. So where did we go from here? So Einstein, we all know Einstein, what he did was he actually studied this photoelectric effect. Okay. And what he found is that if I were to take this photoelectric effect and look at my light, what I will see is that that's going to cause a, if I were to take that and look at my light of sufficient frequency, what I'm going to see if I'm shining it on a metal, that's going to cause a current to flow. So there's actually going to be energy moving from one side of that metal to another. So there is current going on. Now, when Einstein was doing this, what he found was that the amplitude of that radiation did not matter. What was important was the frequency. And so this told him that the light must be in the particles, okay, each having a given amount of energy. And so what he did was that he proposed that energy equals Planck's constant times that frequency. So he completely took out that integer. And so in the grand scheme of things, what he found was that we can actually take that formula, energy equals Planck constant times frequency, and we can actually combine it with our original speed of light equation. So energy equals Planck's constant times the speed of light divided by our wavelength. And that way we would automatically be solving for our frequency, okay? Or we would actually have a wavelength to use for our frequency to solve for energy. Sorry, that was kind of a whole jumble of things. Now, when we do this, that's going to tell us the amount of energy in a single photon, okay? But sometimes we're not looking for a single photon. We want to know how many photons we actually have. And so this would be the formula that we use for the number of photons. Basically, the number of photons, which we would use as N, equals the total energy divided by the energy per photon. So we can solve for the energy per photon and then divide that from our total amount and get the number that we have. Okay? So here's an example of that. So it says a nitrogen gas laser pulse with a wavelength of 450 nanometers contains 4.75 millijoules of energy. How many photons does it contain? Okay, so what do I need to do for this? Well, first off, I need to solve for my energy. Well, my energy equals Planck's constant times speed of light divided by my wavelength. Okay, so my energy equals Planck's constant 6.626 times 10 to the negative 34th joules times seconds times speed of light 3.00 times 10 to the 8th meters per second. And then my wavelength is 415 nanometers. Okay. Well, I need to convert my nanometers into meters. I'm actually going to zoom in over here. I did run out of room a little bit. So my nanometers into meters, I know that there are 10 to the 9th nanometers for every meter. So let's cancel out all of our units. So meters, meters, nanometers, nanometers. We've got seconds and seconds. We are going to be left with joules. Okay, good, because that's what we want, right? Energy. So I'm going to take that. I'm going to plug that into my calculator, and I'm going to find that the energy of a photon is 4.79 times 10 to the negative 19th joules. Okay, so now I know the energy of a photon, but my question asks me how many photons does it contain? So what do? My number of photons equals my total amount of energy. So my total energy was 4.75 millijoules divided by the energy per photon, joules. We're going to convert from millijoules into joules. Cancel those out. We know that there are 10 to the 3rd millijoules for every 1 joule, or 1,000. We're going to plug that into our calculator, and we will find that we have 9.92 times 10 to the 15th photons. So that would be our final answer. All right, y'all, so that is it. We are done with Unit 3. Please let us know if you've got any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.